there are so many things to worry about, so many things to be concerned about. There are many troubles in the world, of course, and these are important, and we need to solve them. But we also need things that make us excited to be alive, that make us glad to wake up in the morning and be fired up about the future and think, yeah, the future is going to be great. And this space exploration is one of those things. And becoming a spacefaring civilization, being out there among the stars, this is one of the things that I know makes me glad to be alive. I think it makes many people glad to be alive. It's one of the best things. So, the critical breakthrough that's needed for us to become a spacefaring civilization is to make space travel like air travel. So, with air travel, when you fly a plane, you fly that plane many times. I mean, the risk of stating the obvious, really almost any mode of transport, whether it's a plane, a car, a horse, a bicycle, is reusable. You use that mode of transport many times. And if you had to get a new plane every time you flew somewhere, and even have two planes for a return journey, very few people could afford to fly. Or if you could use a car only once, very few people could afford to drive a car. So the critical breakthrough that's necessary is a rapidly reusable orbital rocket. This is basically the holy grail of space, and the fundamental thing that's required. And it is a very hard thing to do. It's only barely possible with the physics of Earth. I mean, if Earth's gravity was a little heavier, it would be impossible. And if Earth's gravity was a little lighter, it would be quite easy. So we're really right on the cusp of what is physically possible. So in order to create a rapidly reusable rocket, and fully reusable orbital rocket, you have to have engines that have incredibly high specific impulse, that essentially are extremely efficient. You need to have a structure that is also incredibly mass efficient. And then that all needs to come back to the launch pad and be able to be refilled with propellant and flown again very quickly, just like an aircraft. So it's just because of the physics of Earth being quite a deep gravity well and having quite a thick atmosphere. This is a tough but not impossible thing. But it is the most fundamental thing. So
we're living at the dawn of a revolution in human spaceflight. In the last decade, since the retirement of the space shuttle, things have seemed pretty static. Humans have used the Soyuz spacecraft to go to and from the International Space Station. We've learned a lot about living and working in space. But while that's been going on, the groundwork has been laid for the next big leap. The next decade, even the next 2 or 3 years, are going to be very different. We're about to enter a new era of using rockets to take humans out into the solar system. So what is it that's about to happen? Where are we going to go? And how are we going to get there? When you're going to space, the first step is the biggest, getting into orbit. And right now, there are only a couple of different ways you can get human beings into orbit. The space shuttle of the United States has been retired for many years. That leaves the redoubtable Soyuz from Russia and the very similar Shenzhou from China. The Soyuz, of course, is what takes human beings to and from the International Space Station. But of course, we don't just need to carry human beings to the space station, we also need to carry cargo. And there's a variety of spacecraft that have been designed to do that job. The first of these is the Russian Progress spacecraft, a sort of automated version of the Soyuz with a cargo capacity of a couple of tons. And over 160 of these have brought cargo to the International Space Station successfully over the lifetime of the project. But it's not just the Russians who are doing this. There are cargo spacecraft from many countries. For example, the Japanese Konotori spacecraft has been part of the project. 8 of these have visited the International Space Station, and the European ATV, launched from the European Space Agency, has made 5 flights atop Ariane launch vehicles. The ATV is nice because it has a very large cargo capacity, over 3 times that of the Progress. The Americans decided, after the shuttle retired, to encourage private companies to develop their own systems to service the International Space Station. 2 companies in particular. The first one was Orbital Sciences Corporation, which developed the Cygnus spacecraft. It's now flown by Northrop Grumman. And then there was the company SpaceX, which was building the Dragon spacecraft, which has made 20 flights. Just recently, it made its 20th flight to resupply the International Space Station. The Dragon has an additional capability that's very useful, because the other cargo spacecraft are simply discarded, jettisoned and discarded, allowed to burn up in the Earth's atmosphere after they've made their flight. But the Dragon can return to Earth, bringing cargo back from the International Space Station. And in fact, a single Dragon spacecraft can make multiple flights to the ISS, and this has been done several times. NASA also had the idea to encourage private companies to come up with human transport vehicles to replace that capability of the shuttle, the so-called Commercial Crew Program. And the first of these is the Dragon 2, the successor to the Dragon, made by SpaceX, which had its first uncrewed orbital test in March of 2019, and will fly with a crew probably in May of 2020. The next of them is the CST-100 Starliner, created by Boeing Corporation, which had an orbital test flight in November of 2019. It will probably have another orbital test flight without a crew sometime in 2020, and a first flight with crew in 2021. Originally, in fact, there were 3 companies in the Commercial Crew Program, but Sierra Nevada Corporation, which was creating the aerospace plane Dream Chaser, did not move on to the final stage of the Commercial Crew Program, didn't get a Commercial Crew contract. But the Sierra Nevada vehicle is still being built for cargo transport without crew. And then there's NASA's own new human-crewed spacecraft, the Orion multi-purpose crew vehicle. It's like an enlarged Apollo command module, and it's designed to take human beings not just to low Earth orbit, but beyond to the moon and farther out in the solar system. The first test of a prototype Orion was done in December 2014. They put it in a very highly elliptical orbit so that it could re-enter the Earth's atmosphere at high speed, and they could test the re-entry system, which worked fine. But to really launch this spacecraft, you're going to need a big rocket. And the intended launch vehicle is the Space Launch System, now being developed by NASA, a really enormous rocket that probably will have its first launch in 2021, late 2021. I want to talk for a minute about SpaceX. SpaceX, Space Exploration Technologies, is a private aerospace company founded by the eccentric genius engineer Elon Musk. Musk made his first billions as one of the founders of PayPal, but since then he's branched out into some pretty ambitious engineering undertakings, including founding the Tesla automotive company and SpaceX. Musk is flamboyant, brilliant, optimistic, and bold. He would be easy to dismiss, except SpaceX has established a solid record of accomplishment and innovation that's just awe-inspiring. In fact, in the great scheme of things, Elon Musk may turn out to be the peer of Wernher von Braun and Sergei Korolev as an absolutely pivotal figure in the history of rocket science and technology. So it's worth taking a look at what they've done and what they're up to now. Among SpaceX's many accomplishments was the Merlin rocket engine, a reusable rocket engine with a good specific impulse and a very high thrust-to-weight rocket motors, one of the highest thrust-to-weight ratios of any rocket motor ever flown. And this is the core innovation behind the Falcon 1 rocket, which they developed to launch small satellites into low Earth orbit, and then more recently the Falcon 9 launch vehicle, which can take 13 tons to low Earth orbit. And of course, we've already mentioned the Dragon, the unmanned orbital vehicle used for resupply missions to the International Space Station. SpaceX learned how to do what seemed to be impossible. They learned how to reuse the large first stage, the booster stage of the Falcon 9, by simply having the booster stage return to the point of launch and land on its rocket motor. They, of course, are building the Dragon 2 and are ready to launch. The first U.S.-launched manned spacecraft since the retirement of the Space Shuttle. And they now have an even larger launch vehicle called the Falcon Heavy, which made its first flight in 2018. The Falcon Heavy has a Falcon 9 core stage with two Falcon 9 strap-on boosters. And it's one of the largest launch vehicles that has ever been launched since the Saturn V, and it is an amazing thing to see.
3, 2, The Centaur will be attempting its landing on the opposite.
This footage goes out when it approaches the...
That final touch, launching a Tesla Roadster with a spacesuited mannequin on an orbit that would take it past the orbit of Mars, is pure Elon Musk. We're going to conquer space, and we're going to have a blast doing it. But that's not the limit of Musk's ambition. The BFR, for Big Falcon rocket, of course, will be as big as a Saturn V, fully reusable, and able to launch 150 tons to orbit. It's powered by the new Raptor engine, running on supercooled methane and liquid oxygen. The first stage, called the Super Heavy, has more than 30 of them. The upper stage, the Starship, has 6, 3 optimized for use in the atmosphere, 3 optimized for space. Like the first stage of the Falcon 9, once the Super Heavy has done its job, it will turn back around and return to the launch site to be refueled and flown again. The Starship continues on to orbit, and when it's done its job, it can return using a fully reusable heat shield made of glass tiles. But orbit need not be its final destination. Other starships, configured as tankers, can refuel the Starship in orbit. With that fuel, it can go on to the Moon, to Mars, or beyond. It sounds like science fiction, but SpaceX is building the prototypes now. The Raptor engine has already flown in a test vehicle called the Starhopper. It doesn't look like much, but its hull is 9 meters across, the same as the Starship. Full-size prototypes of the Starship have been built and tested on the ground. The next step is a flight test, a hop up to 20 kilometers and back. It is entirely possible that the first operational Starship vehicle will go into Earth orbit within the next 2 years. Once that happens, once we can raise 100-ton payloads to orbit for the cost of the fuel and then reuse the launch vehicle again and again, then everything changes. Then we really can become a spacefaring civilization. The ambitious plans of SpaceX are based on a theory of innovation. Elon Musk thinks that the way to learn how to build and fly rockets is to build and fly a lot of rockets, to try things out, to experiment, to learn how to do difficult things by trial and error. He thinks that this was the key to the burst of innovation in the 1950s and 1960s in rocket technology and space exploration. Now, SpaceX is not the only, even private company doing something like this. For example, Jeff Bezos' company, Blue Origin, has built and flown its own reusable booster and is working on an orbital vehicle with very impressive capabilities. But that just makes the point all the more extreme. We're on the cusp of the next space age, an age in which we'll be able to go much farther than we've ever gone before. So we want to go to the moon, or Mars, or anywhere really. How far do we have to go? Well, there are two sensible ways to answer this question. And the first is travel time. How long will it take to get there? How many days, or weeks, or months, or years will it take? And that will affect all kinds of things, like the life support requirements for our spacecraft, the requirements for the health of the crew, for radiation exposure, and so on. And the second way to answer that question is to talk about delta V. And the delta V required for the trip affects the propulsion requirements. And if we can't solve the delta V problem, we can't even begin to solve the travel time problems. But if we're clever, there are ways we can get delta V for nothing. The first way is called a gravity assist. If we have a flyby of a moving planet or moon, we can actually use its gravity to increase or decrease the specific energy of our spacecraft. If we fly past it one direction, we can gain speed. If we fly past it on the other side, we can actually lose speed. Only certain geometries work, but it's a nice, efficient way of getting delta V for free. And another way is a free way to slow down. If we're going to a planet that has an atmosphere, we can actually pass through the outer atmosphere of the planet and allow our spacecraft to dissipate some of its specific energy via friction. Now we need a heat shield to do this, but we can use this, for example, to go from a hyperbolic orbit into an elliptical orbit about the planet. Another nice trick is something called the Oberth effect, named after its discoverer, our old friend Hermann Oberth. Our engines can produce a given delta V, a given change in speed. But what we really care about is how that changes our orbit through space, and that will depend on how much our energy changes. And a given delta V can produce a larger delta E when the spacecraft is already going faster. So let's take a look at an example. Let's suppose we're going at 1,000 meters per second. We fire our rocket motors and come to go at 1,100 meters per second, a delta V of 100 meters per second. If we calculate delta E, we actually get something like 100,000 joules per kilogram. But suppose we start out going 5,000 meters per second, and once again, we use the same amount of rocket fuel to increase our speed to 5,100 meters per second, a delta V of 100 meters per second. Then delta E is not 100,000 joules per kilogram, but 500,000 joules per kilogram. More bang for the buck. And so the moral of that story is that it's most efficient to make our orbit changes when we're going fast, say when we're passing close to a planet or a moon. That's when we get the greatest orbit change for a given delta V. This is a delta V tree, a way of visualizing delta V requirements for space travel near the Earth. This one was drawn by Hollister David. The numbers on the branches show delta V requirements in kilometers per second. The red vines show us opportunities for aerobraking if we go in the direction shown by the leafy arrows. For example, to get from the surface of the Earth to low Earth orbit, we need a delta V of about 9.7 kilometers per second. That's a little higher than we said before, but it's about right. Using the Earth's atmosphere to slow down, on the other hand, we can return from low orbit with very little delta V required from our rocket engines. Alternately, from low orbit, we can get to the surface of the Moon for a delta V of 5.9 kilometers per second. The Moon has no atmosphere, so rockets are the only option for landing. 3.6 kilometers per second would be enough to put us on a Hohmann transfer orbit to Mars. Once there, we would need 6.5 kilometers per second to land directly on the surface. But it is much easier to allow ourselves to be captured by Mars, less than 1 kilometer per second for that, and then use the thin atmosphere of Mars to slow down for a landing. Coming home, we can use aerobraking at the Earth end, but even so, it takes about 7 kilometers per second of delta V to make the trip. Even the most optimistic delta V for a Mars mission, getting to Mars and back to Earth, is about 21 kilometers per second. That's a huge delta V. And of course, Tsiolkovsky's equation tells us that the mass ratio required to achieve a certain delta V increases exponentially with the delta V required. So it seems to make a trip to Mars and back impractical. But there are some ideas that we might use. For example, we might send extra fuel and/or a crew return vehicle separately, send that to Mars, and then use it to come back. If you've seen the recent Matt Damon movie, The Martian, great movie by the way, then that's one of the strategies that set of missions to Mars employed. Or here's another idea. We could produce the return fuel locally. That is, we could use a small nuclear reactor or solar panels to create methane and liquid oxygen from carbon dioxide and water, both of which are found on Mars. This was the concept that Robert Zubrin used in his very influential Mars Direct proposal in 1990. And of course, this is why the SpaceX Raptor engines are designed to use methane and liquid oxygen. The return fuel from a trip to Mars can be manufactured on Mars, given a source of energy. And of course, there's a third idea. And the third idea is, don't return at all. Just settle Mars permanently. Now, if we decide to go this direction, make a one-way trip to Mars, the delta V requirement is much less, and we can take a lot more stuff that way. But it means we can't come home. There are other possible destinations besides Mars. A few of them are shown on the delta V tree. One destination is one of the Lagrange points. These are co-orbiting points in an orbital system, the Earth and the Moon, or the Sun and the Earth, that remain relatively stationary as the bodies orbit each other. L4 and L5 on the Moon's orbit ahead and behind are stable points. A spacecraft placed near there will stick around. L1, L2, and L3 are stationary but unstable, so you'd need to use a little rocket fuel from time to time to maintain your position. But L1 is an especially favorable launch point for interplanetary trajectories, so it might be a good idea to build a space station there. Lagrange points are just the tip of the iceberg. Orbital mechanicists have mapped out a whole complex set of shifting, gravitationally assisted trajectories, sometimes called the Interplanetary Transportation Network. Using chaos theory, you can finesse your way around the solar system for amazingly little fuel. Some robot probes have done this. Unfortunately, the trajectories in the network often take a long time, decades or even more. Some of the most intriguing possible destinations are the near-Earth objects. Now, most asteroids in space are located out beyond the orbit of Mars, far away, but a good number of them have orbits that take them near the Earth. We know of at least 1,000 that are more than 1 kilometer across. In delta V terms, these can be relatively easy targets. Depending on the timing, the requirements for a round trip to a near-Earth object are less even than a trip to the Moon. So why would we go? Well, there are a lot of possible reasons. Scientific exploration, of course, but also hazard mitigation. Some of those NEOs might someday hit the Earth with disastrous consequences. An asteroid impact killed off the dinosaurs 65 million years ago, and we'd like to learn to avoid their fate. Asteroids are also promising targets for resource prospecting. It's been estimated that a modest-sized asteroid contains $1 trillion worth of platinum and other heavy metals. We might even find a way to transport a small asteroid back to the Earth-Moon system for use as raw material for our orbital projects. Now, people have been BSing about all the great things that we're about to do in space for most of a century. But this moment in history feels different. And the reason is the revolution that's already happening in our access to low Earth orbit. As one science fiction writer said, low Earth orbit is halfway to anywhere. It's the big step. There's no way to finesse it. There's no fancy gravitational assist. There's no way of using super efficient low thrust ion engines. No, we need rockets. But we're getting good at rockets. And if all this is true, then the human future is not going to be confined to the surface of the Earth. Konstantin Tsiolkovsky, our old friend, once said, "The Earth is the cradle of mankind, but one cannot live in the cradle forever."
The reality is, as far as we know, this is the only place, at least in this part of the galaxy or in the Milky Way, where there is consciousness. And it's taken a long time for us to get to this point. So what I'm saying is that it appears that consciousness is a very rare and precious thing. And we should take whatever steps we can to preserve the light of consciousness. And the window has been open only now. After 4.5 billion years is that window open. That's a long time to wait, and it might not stay open for long. I'm pretty optimistic by nature, but there's some chance that window will not be open for long. And I think we should become a multi-planet civilization while that window is open. And if we do, I think the probable outcome for Earth is even better, because then Mars could help Earth one day. And so I think we should really do our very best to become a multi-planet species and to extend consciousness beyond Earth. And we should do it now. Thank you. Thank you.